Well, welcome everyone to this webcast. My name is Rhys Bowley and I'm one of the engineers at National Instruments, working in particular on wireless communications in education. To give you a bit of background on myself, I studied my Masters in Electronic and Communications Engineering at Cardiff University. I spent a little time there working in the research labs, looking at mobile phone power amplifier characterization, and I've been with NI for a few years now. So I realised that for part of this presentation I will be preaching to the converted, setting the scene, if you like, for why it is that we're talking about wireless communications in the first place. Then I want to go on to discuss a piece of hardware in particular called a software-defined radio. We'll look at exactly what that is. I then want to talk to you about software-defined radios at National Instruments, and then look at some of the teaching material that we have based around those. I don't want to just run you through slides, I also want to actually show you some of this in action. So I'll demonstrate that a little later on, and then I'll tell you exactly how you can get hold of some of this for yourself. And there will of course be time at the end for questions. I've got a couple of helpers with me here as well, and we'll be able to actually answer questions as we go through using the chat window on the side. So do let me know as we go along if you have anything you want to ask. And before we get into the details, let's get a feel for just how important wireless communications is to us now and will be in the future. We've always got to keep one thing at the back of our minds, and that is that we have to do more than make our students experts in what was. We need to make sure that they can be effective in the world of tomorrow. We probably all are old enough to remember a time before everybody had a mobile phone. And furthermore, before mobiles could even use the internet. And then, even when they could, it was all plain text and scrolling web pages. Now I can stream video and audio of a live sports game in high definition whilst on a moving train, or whilst my emails, social media, and everything else stays connected in the background. But you've heard this before, right? You see, that's the thing the world often misses about wireless communications. It's so much more than just mobile phones. Everything's becoming connected these days, and it's not just the consumer space either. I recommend checking out some of the amazing work being done by Airbus on their Factory of the Future, where the entire design, manufacture, and maintenance ecosystem is connected, all the way down to the technicians' hand tools and augmented reality glasses that feed live data into both the jobs list for that day, as well as the quality assurance database. It's truly mind-blowing. Furthermore, wireless will affect every future engineer. Low latency, high data rate connectivity is doing more than just letting us connect existing things together. It's completely changing the very design concept in areas that we've never really considered. Wireless communications is more than just the realm of the RF guys now. Let me make an analogy to something we're all used to, and that's the everyday car. In the advent of low latency, sort of 1 millisecond 5G communications links, we're now looking at a real possibility of totally driverless cars communicating vehicle to vehicle. Now, whilst the idea might seem a little bit strange, there's some undeniable benefits if we were to all go driverless, like fewer traffic jams and no more asking for directions or taking wrong turns. And especially considering more than 1 million people die annually in road traffic collisions, they could be the greatest advancement in health of this century. But let's have a think about how the capabilities of wireless has affected the automotive engineer. Aside from needing to lay perhaps some new communications protocols, that is, if a driverless car is driverless, does it need a steering wheel? or pedals for that matter? How about a windshield? In that case, do people even need to be sat facing forwards? You don't get any of these things as a passenger on a train, right? And anyway, what is forwards anymore? Does the car even need a front and a back? If all the cars were driverless, do they need to have powerful headlights in the same way as we do now? You see where I'm going? We've changed the very design concept. Engineering students of all backgrounds need to have at least a basic grasp on wireless communications and its capabilities if they are going to be effective designers in the modern world. The way I see the future of wireless communications education is as the circuits class of the future, where all engineering students sit it during their first year. Just like the way that electronics revolutionized all engineering design, and nowadays it's in everything, the future holds the same for wireless communications. But let's bring it back to our topic, which is enhancing education with SDR. So what is SDR? Well, the acronym stands for Software Defined Radio, and a radio is simply a tool we use to make wireless communications links. A radio basically does two things. One is that it builds information into a message signal, and that's called modulating. And then it scales that up or down into a high enough frequency range that it will travel through the air, and we call that up or down conversion. The order in which we do these two things depends on if we want to transmit or receive. Traditional radio transmitters and receivers build the message signal using hardware and real-world components. That's a bit of a pain if you want to experiment by building a different signal than what you were originally designed for, and that's part of what's been holding back researchers who need to prototype in the last few decades. Redesigning hardware is slow and expensive. A software-defined radio, however, is a device which does the up or down converting and analog to digital conversion in hardware, but uses software on a PC to do all of the modulation side of things. This approach is very powerful, and in the teaching space, it means that students can transition quickly from theory to simulation and into design and experimentation with real-world signals. So why aren't these architectures everywhere then? If this approach is so powerful, why isn't it the standard for teaching communications? There are two main reasons: cost and complexity. It was barely more than a decade ago that powerful software-defined radios were reserved to the areas of military research, and their cost was prohibitively expensive. Added to that, the existing software tools required programming expertise and were worlds apart from being ready to use in teaching. The NI USRP is a family of software-defined radios that aims to address both of these problems. They cost orders of magnitude less than the large RF systems often found in research, and are programmed using LabVIEW, the graphical nature of which has been proven in teaching time after time. NI has had USRP hardware since 2010, but in the last year we've made huge advancements in this area, in the form of new hardware devices designed specifically for teaching, which cost less than half of the previous models, and LabVIEW Communications, a new version of LabVIEW designed specifically for making modern communication systems. These new USRP devices designed for teaching, they are the NI USRP 2900 and 2901. They have continuous frequency range from 70 MHz through to 6 GHz. Now that means that you can experiment with everything from FM radio stations through mobile, ISM and Wi-Fi bands. They connect your PC or laptop using USB, and you can even power the devices using USB 3 port, meaning you don't have to plug them into mains power. The 2901 has 2 input and 2 output channels, so you can even investigate 2x2 MIMO architectures with a single device. These are also our smallest and lightest USRPs yet, so we've put a Kensington lock slot on them in case you want to make sure they stay in the teaching lab and don't go walkabout. Now, we don't expect you just to throw these systems at your students and to have that all of a sudden revolutionize the way that you teach. We want to provide a complete teaching solution. So on top of our hardware and software, we also offer ready-to-run course material and lab manuals. We currently have 2 course manuals that you can buy bundled together with NI USRP hardware. These lab manuals come with all of the solutions and exercise code, and we're able to support you directly through our worldwide support channel. Now, the first manual is Introduction to Communication Systems, written by Professor Bruce Black at Rose-Hulman Institute of Technology. This course is directed towards undergraduate students, and it covers the basics of wireless communication, including analog and frequency modulation, all the way through digital concepts such as QPSK. Now, this is where I would start communications for undergraduates on, say, a EE degree scheme, maybe in their second year, after they've had some kind of signals and systems class. Now, no LabVIEW skills are required of the students before they start this course. The second manual is Digital Communications by Professor Robert Heath of the University of Texas. Robert focuses on the OFDM modulation scheme, which is the underlying technology behind 4G or LTE mobile phone signals. The students learn from the point of view of a system designer, starting out with a complete working OFDM system and then slowly removing subsystems and replacing them with their own code, thus experimenting with different techniques. This course is targeted further up the curriculum and is suitable for, say, final year undergraduates with some previous LabVIEW and wireless communications exposure, or maybe for a master's course focusing on communications engineering, for example. So let me show you one of the experiments from these manuals in action. Now, what I have here is my completed solution to lab number 12 in Introduction to Communication Systems. Now, this lab is the QPSK lab. QPSK, or Quadrature Phase Shift Keying, is one of the more popular modulation schemes that comes up in textbooks. I think some of the reasons behind its popularity is really it's one of the first modulation schemes that allows us to introduce students to the eye diagram and concepts like bit error rate. I have 2 pieces of code in front of me. This first one here is the transmitter code, and the second one is the receiver code, but I'm going to be running both of these at the same time on one USRP device. If we take a look at the graphical code behind these systems, you can see the constituent parts of a receiver chain starting to form. So here we have some basic hardware configuration and setup with information such as the IQ rate and carrier frequency, amplification. Then what we do is we define ourselves a bit stream of information. We then map that bit stream using this constellation map here, and as we move on, we then apply a pulse shaping filter. Now, this is actually going to help improve the amount of spectrum that we use when we transmit this signal over the airwaves. And before we send it out, we build up a visual representation on the user interface so that students can verify and see exactly what they've built throughout the rest of the transmitter chain before we send it out. Then we commit that signal down to the USRP hardware and start transmitting it. Once we're done, we close off any reservations that we may have had open previously. So if I set this running, what it'll do, it'll just take a little time to build that signal up, then commit it down to the USRP hardware, and we can see exactly what we're transmitting there. We get a baseband representation of our signal, and I can just use the map tools to zoom in on that. What you'll start to see is we get that characteristic QPSK phase shift happening within our sinusoid here. And we can also take a look at the frequency domain version of what we're sending. Again, if we just use some quick graph tools, we can make a quick verification on roughly the bandwidth of what it is we're sending. And that looks to be in around about the sort of 200k range after we've applied that pulse shaping filter. Now what we can do is switch over and run the receiver code. And what we should see is that once the receiver has received and analysed the data, we get the same baseband output with a little bit of real-world distortion added. And we also get this representation of our error. Now, this is something I really like because I think we do students a bit of a disservice in some of the communications concepts that we cover, especially something like bit error rate, which we quote as just a single number. But in fact it's a time-varying quantity, and it varies for all kinds of reasons, things like real-world effects, time-varying differences in the hardware, and all sorts of things. Even the modulation scheme and the bit stream have an effect on this. Now students can actually experiment with different bit streams, different modulation schemes, and then visualize that time-varying error. And they can also just run the experiment again and see how it differs. Now below that you can see the eye diagrams, both equalized and raw, and you can see that I have a fair bit of optimization to do in my communication system. I should probably move my aerials so they are right next to each other. If we take a look over here, actually we can see that the bit error rate isn't that bad considering our eye diagrams. And finally we can see our constellation plot here. Now we can roughly make out in terms of density that there are about 4 symbols here, but they're really quite squashed together, so I need to work on perhaps my signal to noise ratio. Now if we want to grab any of this data for our report afterwards, we can do that. We can just right click and capture that data. See it appears here. We get an interactive version which we can manipulate. We can head over to the transmitter side of things and do exactly the same, even whilst the code and transmitter is still running, and then we can manipulate this data to however we so want it in order to prove that we really did send out what we were supposed to. So how can you get your hands on some of this material? Well, starting with the software side of things, LabVIEW Communications System Design Suite has a free evaluation on NI.com, and it's already included in our academic site license. So if you have a site license at your university, then you can just get this downloaded and installed and activate as normal. The NI USRP teaching bundles comprise of 2 USRP radios and 2 hard copies of the course manuals. Now that means that you can get 2 ready-to-run lab stations starting at under $2,000 for the pair. You can also do a one-time only low-cost purchase of just the USRP hardware if you're interested in evaluating it and you want to see if it's going to fit into your scenario and suit your needs. And then furthermore, we are more than happy to talk to you about getting some of this material. Now there's 2 ways that you can get in contact with us that are the best. One is to call your local NI office if you look for the contact us section on ni.com, and the other is to spend some time with a local NI field engineer who can actually demonstrate some of this on site with you. So that leaves us just enough time for some questions. If anyone would like us to perhaps cover something again, or you want to ask us some specific questions, feel free to do that now. Otherwise, it just remains to me to thank you for taking the time out of your busy schedules. I know that feeling very well, and hopefully we'll get to see you again soon.